Hi, welcome to the next lecture on power spectral density. So as promised in previous lecture, I will be proving or give a sort of outline of proof how we define power spectral density in an alternative way. Now, first of all, I would like to recall, as you all of you might be knowing, that if you have a stationary random process, autocorrelation function is defined in this way. So I hope that you are all well aware of stationary random process, but for those of you who might have forgot, I will little bit give some brief idea of stationary random process. So you know random variable, right? Now if random variable is a function of time, so at each point of time it is a random variable, right? And the problem will be if you find the mean of this random process, which is actually a time function of a random variable, then its mean, suppose mu of t, will vary at every point of time, right? Similarly, if you want to find how correlated a process at time t1 is with the process at time t2, right, this quantity depends upon time t1 t2. So hence for different times we may have different means. Now imagine that if t is continuous, so if 0 suppose less than t less than some capital T, so how many points are there? There are infinite time samples. So we need to know mean at infinite number of points. We need to know this quantity correlation at infinite number of times, which is not possible. So in practice we assume that process is in some sense stationary, means that the mean does not depend on time, although process is random and it varies with time, but mean does not depend on time. And other assumption we have that if I take a sample at time t of this random process, other sample I take at t plus some tau is a fixed constant, and then I take the mean of this. Now this quantity is actually correlation between the process at time t and at time t plus tau. Then for stationary process, especially Whiteson stationary, we say that this quantity depends only on the difference of time. So on time scale, if this is t and if this is t plus tau, so for all t, as long as the next sample is tau times apart, the autocorrelation function, this we call as autocorrelation function, this will not change. Now you observe one thing, that autocorrelation function is product of same random process with itself at two different times. So when you take product of signal with itself, suppose if you have non-random deterministic signal x of t, you multiply it with x of t, it becomes x square of t. So this x square of t gives a notion of energy in the signal or power, right? So this is very important observation. Now what we do is, if this is now autocorrelation function, which in some sense gives us the measure of average power also, then its Fourier transform, if you take Fourier transform of autocorrelation with respect to the time difference tau, the resulting Fourier transform, which will be the frequency information of this autocorrelation, so it is called power spectral density. Okay, now if you see closely, for for this integral to converge, you need, if you recall the conditions of Fourier transform, you need that this x of t or any signal whose Fourier transform you are trying to find, you need that should be integrable. That is, this absolute value of this integral should be less than infinity. But practically, if you take the signals, which suppose a signal of this type, which is having values for all time, okay, infinite duration signal, then definitely we cannot satisfy this condition, because if duration is infinite, this integral will not be less than infinity. So how to handle that? We construct a truncated segment. Okay, we construct a truncated segment of x of t. What does it mean, truncated segment? So let me again, suppose we have a signal like this. So here is x of t and here is a t, right? So we have a signal which is varying okay, throughout. Now I will just do one thing. From minus t to t, I will just take this much part. So I will just take this much part. This signal I will denote by x subscript capital T of t. This is called a truncated signal. Now definitely this signal is of finite duration, and its energy will be finite. Okay. So now for this truncated one, first of all, how I define it is here. You define it as it is equal to x of t whenever time is between minus capital T to capital T, otherwise it is 0. Okay, and we define capital X subscript T of f as it is Fourier transform. Okay, Fourier transform of truncated signal, and clearly this is a finite duration signal. Its integral will be finite, hence its Fourier transform exists. Okay, you should recall the properties of Fourier transform. Now we have an important theorem which is called Parseval's theorem. It's also called Rayleigh theorem in some books, which actually says that, see, what is this integral? Okay, sorry, it should be minus infinity to plus infinity. Okay, there is one typo here. So what should be this integral? Yeah, sorry. So now I corrected the typos. So you look at this integral. It is a measure of total energy in a signal. You know that square of a signal is the measure of instantaneous energy, and if the signal is time varying and you integrate it over all the time, then actually square of a signal will give a notion of power, right? And integral of power, instantaneous power with respect to time. So I should go back here just a moment. So I will tell you briefly. So crudely, in basic physics also. So power is energy per unit time, right? So if we see that a power, instantaneous power, that is power arbitrarily varying with time. Okay. So from this relationship we get energy is power into time. But if power is varying at every point of time, then energy is, right, integral. Okay, and in fact we can see from this, suppose if you are considering a signal a time duration of suppose minus t to t, right? So you can define the average power as e divided by t, or some books even take it as 2t. Okay, energy per unit time, that will be the notion of average power. So we'll see it. So this is energy, and Parseval's theorem says that energy, in time domain, that is if you use a time domain signal to compute the energy, is same as energy in frequency domain, that is if you use a frequency domain, so here this xt of f square df integrating over all the frequencies, this is also measure of energy. Now since xt is a truncated version, it is 0 outside minus t to t, so you can write it as minus t to t, x of t whole square. It's mod. So I am taking mod because this will work even if signals are complex. Okay. Now for a random process, when the signals are random, this quantity, this quantity and even this quantity, it will be random quantity. So we would like to take expected value, average. So average energy is given by expected value of this integral, right? Now what will be the average power? So average power will be 1 by t expected value of minus infinity to infinity xt of f df. Okay, so I think I should make one correction here. Okay, so there was one more small typo. I corrected it. The typo was that I should define signal from minus t by 2 to t by 2, so that the total duration is t. Okay, we can even do it from minus t to t, so the total duration will be 2t. So why do we do that? Because now I want to define average power. So I will again recall you this thing. Average power is energy per unit time, average energy per unit time. Now the total time duration is capital T here, right? So this is minus t by 2 and this is t by 2. So the total duration of time is t. So what we will do is we'll divide by t this expected value of energy. But now we had truncated this signal, right? Okay, so you will have one question in the mind that, so you truncated the signal. So our original signal, suppose it is like this. Now I truncated it from minus t by 2 to t by 2, and I am finding energy for this. But I need to find power for this. I need to find power for the whole signal. So what I will do is I will increase this t. I will make this t goes to infinity. So when I will increase this t, I will be eventually including all the samples. Now what is the benefit of this? You will say the benefit is that before you take the limit t goes to infinity, this quantity is easy to compute. Okay, the integral exists and integral is finite. We can find it. Once you have computed the integral, the resulting thing will be function of time. Okay, and for nice signals this limit exists. Okay, hence we can find the average power. This is the total average power. Okay, now let's look at it in a different way. So here is the average power formula. We say limit t goes to infinity 1 by t expected value of this energy. Now this energy is written in terms of the Fourier transform of truncated signal xt of f. Okay, now I am here now exchanging the limit. I am putting this integral out and taking this limit inside. These operations are not so obvious, but I will not go into that discussion in your class. So they are a little bit more involved. It is not always valid to exchange limit and integral. We need some conditions to be satisfied by the function, boundedness and monotonicity, but I will not go into that. Let's assume that the signal is a nice signal and we can exchange. And what we have done is expected value goes here. So it is now limit t goes to infinity 1 by t expected value of square of the signal, right, which is the mean square of the signal. So this expected value of this quantity can also be as a notation wise written as this bar. Okay, so as some of you might be knowing that we write x bar as expected value of x. Okay, so we write x square bar as expected value of x square. Okay, in that notation. So I have here expected value of this that I can write as x bar divided by t. Now what is this quantity inside? And then there is df. So if you look at the example which I gave in the last, I think, doubt session, that if you have density of any particular object d rho and you integrate it with respect to the volume, okay, then the resulting quantity is the mass, right? So whatever will appear in front of this differential operator, that we will define as density, mass density, right? Now you come back to this. If you look at this quantity, so this is the total power. Okay, nice, and we are integrating it with respect to frequency. So this quantity has a dimension wise, it is in some sense some power per unit frequency, or it is the density of power with respect to frequency, or it is power spectral density. So hence we define power spectral density as, see, in some books its notation will be sx6 of f. I am following here, trying to align my notation with the Rappaport. So we defined as px of f, p power x the signal which we are for which we are finding PSD, and f is the frequency. So it is defined as limit t goes to infinity the mean square value of signal in Fourier domain divided by the time, then taking this limit t is equal to infinity. Now you come back, if you recall that when we did the previous lecture, or we took the signal as w of t. So for w of t the notation will be, instead of px it will be pw of f, instead of xt of f it will be wt of f. So this is the PSD. So now in this short lecture I have given you the complete justification of why in previous lecture we defined the quantity power spectral density the way it was defined. Okay, that is mean square of Wt truncated Fourier transform of signal divided by the time duration and then taking the limit to infinity. In next lecture we will now try to find power spectral density for some real modulation scheme. Thank you.